On a very high level, a 3D rendering algorithm has to solve a simple problem. Given coordinates in 3D space, what coordinates correspond with them in 2D space? When looking at most mainstream games, one common denominator becomes obvious very quickly. Almost all of them use an approach called 3D polygon rasterization. The rendering engines execute a series of coordinate transforms to simulate what a bunch of 3D polygons would look like from a certain perspective. While polygon rasterization is quite efficient, certain things like photorealism are hard to achieve with this approach, as it is not analogous to nature's way of doing things. If more realism is desired, a better approach is available: ray tracing. During its exposure to the general public, the concept seems to have accumulated notoriety for being mysterious and extremely hard to understand technology that us mere mortals have no capability of grasping. And I mean, the solution to the problem of real-time ray tracing is just on the edge of our technological reach, so the notion is painfully accurate. However, that notion is only true when a key criteria applies: real-time. In this video's imaginary world, being real-time isn't a requirement. If we're ready to make some trade-offs, mainly measuring performance in seconds per frame instead of the usual frames per second, ray tracing as a concept becomes quite straightforward, actually. In this video, I will show you the core concepts behind ray tracing, as well as walk you through the journey of implementing a ray tracing renderer from scratch. To begin with, what is light? On a microscopic level, light consists of photons. The behavior and interaction of each individual photon can be accurately described with a few equations and laws. For example, the Lambertian cosine law describes how light scatters off a surface. Snell's law describes how light refracts in a medium interface. And Fresnel's law tells us how much a surface reflects based on the angle of the incoming light. Simulate light, and you can simulate what the scene looks like to an observer. After all, what do we see but the light entering our eyes? This is exactly what ray tracing is based on. We can just fire off many light rays originating from light sources and then keep track of, or trace, what happens to each of them. Some will hit objects in the scene and bounce off in multiple ways, while others will wander off the voids of 3D space. However, the prevalent method used in ray tracing does everything backwards for performance reasons. Instead of simulating light being emitted from light sources like in real life, anti-rays are fired from the observer's perspective. These two approaches are exactly equivalent in terms of end results, but by using anti-rays, or backwards ray tracing as it's called, we only have to model the light that directly contributes to the rendered image. How do we go about building the image then? Where do we start? The first order of business is to get some pixels drawn on the screen. For what it's worth, setting up a drawable window in C++ is quite a hassle, especially with its sophisticated dependency management system. I don't think installing SDL should take 3 hours. We don't even need anything complicated, just the ability to set a pixel to a certain color. Anyway, after having sorted that out, it's time to code some of the core building blocks of our renderer. For example, we need to implement a ray class for representing rays. A vector form ray is defined by an origin point and a direction vector. When the direction vector is multiplied by a variable t in the positive numbers range and added to the origin, we get all the points belonging to that ray. To orchestrate all of the work, a scene class will contain all information necessary for the renderer to work. Finally, we also need some geometric shapes to render. A solid choice for the first geometric primitive is the triangle, which is defined by 3 vertices. Theoretically, with those vertices, we could do some fancy math and calculate a formula for determining if said triangle intersects with array. Here, in the real world, apes with their monkey brains accustomed to short-term gratification will much rather copy such information from the best friend of a programmer, Stack Overflow. Either way, said formula is based on the fact that a triangle is just part of a plane. First, we can calculate the intersection points on the corresponding plane, and if the ray and the plane intersect, a finer check can be done to determine if the intersection point is inside the edges of the triangle. At this point, we're almost there to draw our first image. However, given x and y coordinates to our pixel buffer, how can we determine what direction to fire a ray in? The problem might seem a bit intimidating at first. I mean, there are seemingly infinite possibilities. Of course, like in almost all of life, the answer is simply to copy nature. Or more accurately, this guy. He was one of the first people to describe the concept of the pinhole camera, or camera obscura, as the cool kids call it. In a camera obscura, or camera for short, light from the scene enters through a pinhole and projects an image of the scene onto the opposite side of the room. It is worth emphasizing that the form image is a mapping from the three-dimensional outside world to the two-dimensional wall. Just by looking at a point on said wall, it's quite intuitive to determine where the light making that point would come from in the scene. In a similar way, a virtual wall, called the viewplane, can mimic this phenomenon in our code. More precisely, the viewplane will be a two-dimensional array of rays, sized the same as our pixel buffer. The origins of all of the rays lie in the same plane, and all of the rays point such that they travel through a common point in space, called the focal point. This way, we can index the viewplane with the x and y coordinates of a pixel to get the ray that needs to be traced. With all that out of the way, it's time to render our first image. It's not going to be anything fancy, no fancy shading, no reflection, none of that. We're going to render one triangle. If a ray hits the triangle, we're going to shade the corresponding pixels red, otherwise we'll make it black. And there it is, looks fancy, huh? At this point, the possibilities for expansion are almost endless. More complex shapes could be added, a lighting system can be implemented, and so on. I will quickly implement two other primitives that yield the highest awesomeness to lines of code ratio, a plane and a sphere. From the perspective of the ray tracer, nothing but the intersection function is relevant. It doesn't need to know anything about the primitive's internal representation or shape. As long as it knows if a ray intersects with the object and where that intersection will happen, it can work with the shape. This is, of course, a textbook example of how polymorphism, one of the four principles of object-oriented programming, can be utilized to manage the complexity of our program. We will have a common superclass called a surface, which all of the different types of objects will inherit from. With this arrangement, each subtype can implement its own intersection distance function that can then be called through a common interface. After coding more shapes, I will quickly refactor our renderer to work on multiple objects in a scene. This is not difficult. For each ray, we just iterate over all of the objects and choose the closest intersection. Now that we can have more than one object, it becomes quite clear that we need a better material and lighting system. For the time being, I'm going to implement a simple lighting model consisting of diffuse and specular reflections. In our scene, now containing point light sources with a position and intensity, every time a ray hits an object, the tracer will check which light sources are visible from that point. Then, depending on the distance and angle to the intersected surface, it will shade the pixel accordingly. From high school physics, you might remember that the intensity of a light source fades with the inverse square of the distance. Combine the distance factor with the Lambertian cosine law mentioned earlier, and we get a basic realistic looking flat lighting. In addition to the aforementioned diffuse component, we can do something cool. Based on the surface normal, a reflection ray can be formed using this rather complicated formula. By making a recursive call to a tracing function with a new reflection ray, we can model specular reflections, or in other words, mirror images. When combined with spheres and other curved objects, the results look very cool. Transparency and refraction can be implemented in similar fashion, although having to keep track of the refractive indices makes the task a little more challenging. Now it's only a matter of combining the different shading components according to some parameters defined in the material object. Now that looks considerably better. So far, we have covered the basic principles behind ray tracing: view planes, geometric primitive intersections, as well as shading. There might be a part 2, where we will look at implementing PB or physics-based materials, importing models from 3D files, optimize our renderer with boundary volume hierarchies, and much more. In either case, I want to give you a sneak peek into some of those topics with a quick cat-will-roam STBI FFmpeg hack. I'd be very grateful for any kind of feedback in the comments, as well as giving the video a thumbs up or thumbs down depending on if you like it. For the time being, enjoy the renders and see you next time.